Welcome to the fourth lecture of module 1. This lecture will be on steady state molecular diffusion in fluids under stagnant and laminar flow conditions. So, before proceeding to this lecture, we will have some recap on the previous lecture. In the previous lecture, we have discussed Fick's first law of diffusion, where for one dimensional diffusion in a particular direction x, we can write the molar flux JAX is equal to minus DAB dCA dx. dCA is the concentration gradient and dx is the distance, and DAB is the diffusion coefficient. The negative signs indicates the drop in concentration towards the directions of diffusion. And then we have seen for an ideal gas mixture, the diffusion coefficient between component A and B, we call the mutual diffusion coefficients are equal, and we can write DAB is equal to DBA. And then we have discussed the unsteady state diffusion, where rate of diffusion changes with respect to time, and we have derived the governing equations containing unsteady state diffusion, and governing equations are del CA del T is equal to DAB del CA del X2 plus del 2 CA del Y2 plus del 2 CA del Z2, and this is known as Fick's second law, and this is frequently applicable in solids and less frequently or limited situations in fluid. So, today we will start with steady state molecular diffusion in fluids, and in this case there are stagnant conditions and laminar flow condition, and also this can occur in two different geometry. One is constant area and variable area. So, today we will discuss only on constant area, and later we will continue with the variable area. So, for constant area, let us assume diffusion in x direction no chemical reaction binary system and under steady state condition. So, then for diffusion of a particular species A, we can write Na is equal to minus C dAB dYA dx plus YAN. Now, if we separate the variables, we can write minus dYA by Na minus YAN is equal to dx divided by C dAB. Now, consider mixture of gases, gas mixture which is at constant pressure and temperature. Then the concentration and diffusion coefficient dAB, these are constant and independent of position. So, we can write the boundary conditions as at x is equal to x1, the mole fraction of component 1 will be YA1, at x is equal to x2, the mole fraction of component 2 YA2. So, using these boundary conditions, if we integrate the previous equations, so we can write YA1 YA2 minus dYA by Na minus YAN is equal to integral x1 to x2 dx divided by C dAB. So, this is equation number 2. Let Na minus YAN is equal to Z. So, then we can write minus dYA n will be dz, and hence d minus dYA would be equal to dz by n. So, if we substitute this over here with the change of limit, we can write Z1 to Z2 dz by z one by n will be equal to 1 by C dAB integral x1 to x2 dx. So, now upon integration, write 1 by En ln Z2 by Z1 is equal to 1 by C dAB x2 minus x1. So, if we substitute the limit Z1, then we can write ln Na minus YA2 n divided by Na minus YA1 n would be equal to n by C dAB into x 2 minus x 1. So, again we can write ln n into n a by n minus y a 2 divided by n a by n minus y a 1 is equal to n by c d a b into x 2 minus x 1, and this will cancel out, and if we rearrange this one, we can write 1 is equal to c d a b by x 2 minus x 1 and 1 by n ln n a by n minus y a 2 divided by n a by n minus y a 1. So, if we multiplied both sides by n a, so these equations will become n a and n a by n. So, this is equation 3. So, this is the final form of the steady state molecular diffusion of a component A through a constant area, and then if we use these equations for a particular case, steady state diffusion through non-diffusing components. So, consider A is diffusing and B is non-diffusing. In this case, since B is non-diffusing, so flux for B component N B will be 0, and the flux for a component A will be constant. Now, if we go back to the governing equation, we can write N A is equal to N A by N C d A B by x 2 minus x 1 ln N A by N minus y A 2 by N A n minus y A 1. Now, since n is equal to N A plus N B and N B is equal to 0 in this case. So, n will be N A. So, this term N A by n will be equal to N A by N A is equal to 1. So, now these equations will become N A is equal to C d A B by x 2 minus x 1 ln. So, this term become 1, this become 1 and this become 1. So, this will be 1 minus y A 2 by 1 minus y A 1. So, this is equation number 4. Now, consider the system is ideal gas. So, in this case we can write the concentration is equal to total pressure P t divided by R t. Mole fractions Y A, we can write partial pressure of component A by total pressure. So, in terms of partial pressure, we can write the earlier equations. N A is equal to d A B P t by R t x 2 minus x 1 into ln P t minus P A 2 partial pressure of component A active divided by total pressure minus partial pressure of component A at location 1. So, P A 1 and P A 2 are the partial pressure at location 2 and 1, and for binary gas mixtures we know that P A plus P B at any locations will be total pressure. So, that we can write P t minus P A 2 will be P B 2. Similarly, P t minus P A 1 is P B 1, and P A 1 minus P A 2 will be P B 2 minus P B 1. From this we can write P A 1 minus P A 2 partial pressure at location 1 and 2 for component A divided by partial pressure of component B at location 2 minus partial pressure of component B at location 1 will be equal to 1. So, this if we substitute in this relation equation 5. So, now if we substitute this P t minus P A 2 by P B 2 and P t minus P A 1 by P B 1, and then if we multiply these equations by this ratio which is 1, we will essentially have N A is equal to d A B P t by R t x 2 minus x 1 into P A 1 minus P A 2 by P B 2 minus P B 1 ln P B 2 by P B 1. So, this is equation 6.1. Now, if we rearrange this equation, d A B P t divided by R t x 2 minus x 1 into P A 1 minus P A 2 divided by P B 2 minus P B 1 divided by ln Pb2 by Pb1. So, this term essentially we call the log mean partial pressure difference. So, we can write PBLM. Then we can write the flux Na will be DAB PT total pressure divided by RT x2 minus x1 PBLM into the partial pressure difference PA1 minus PA2. So, this is equation 6.2. Now, consider carbon dioxide is diffusing through non-diffusing air under steady state conditions at a total pressure of 1 atmosphere and temperature 300 Kelvin. The partial pressure of CO2 is 20 kilopascal at one point and 5 kilopascal at other point. The distance is given between the 2 points is 5 centimeter, and we have to calculate the flux of CO2. The diffusivity at a particular condition is given CO2 air 2 into 10 to the power minus 5 meter square per second. Let us assume ideal gas and component B air component air is considered as B. So, we can write the flux equations of a component A through non-diffusing B. We can write flux of CO2 is equal to d CO2 air divided by RT x2 minus x1 PT by PBLM into PCO2 at 1 minus PCO2 at 2. The data which is given is diffusion coefficient, total pressure, R and T are known, this distance between the 2 points are known, partial pressure were given, we have to calculate PBLM. So, let us consider the CO2 air, which is 2 into 10 to the power minus 5 meter square per second. PT total pressure is given 1 atmosphere, which is 101.3 kilopascal, which is 1.013 10 to the power 5 Pascal. T is given 300 Kelvin. x2 minus x1, the distance between the 2 points is 5 centimeter, which is 0.05 meter. Partial pressure of CO2 at point 1 is 20 kilopascal, is equal to 20,000 Pascal. Partial pressure of CO2 at point 2 is given 5 kilopascal, which is 5,000 Pascal, and R is known to us 8314 in SI unit Pascal meter cube per k mole Kelvin. And then we have to calculate the PBM. PB1 is Pt minus partial pressure of CO2 at point 1, which is equal to 101.3 minus 20 kilopascal, which is equal to 81.3 kilopascal. Pb2 Pt minus PCO2 at point 2, which is 101.3 minus 5 kilopascal, which is 96.3 kilopascal. So, putting this value, we can calculate PLM, which is Pb2 minus Pb1 by ln Pb2 by Pb1. So, putting the values, 96.3 minus 81.3 divided by ln 96.3 by 81.3 kilopascal is 88.59 kilopascal. So, which is equal to 88590 pascal. So, now if we substitute in the flux equations NCO2, we can write this is diffusion coefficient 2 into 10 to the power minus 5 meter square per second, and then the total pressure 1.013 into 10 to the power 5 pascal divided by R 8314 pascal meter cube per k mole Kelvin into 300 Kelvin, the distance 0.005 meter into the log mean partial pressure difference is of component B 88590 pascal into 20,000 partial pressure of component A at point 1 minus 5000 pascal. So, this will cancel out and this will cancel out. So, if we calculate, the flux will be 2.75 into 10 to the power minus 6 k mole per meter square second. Now, consider the other case where steady state equimolar counter diffusions is occurring. If there is a equimolar counter current diffusion, for our governing equations, as we know, Na is equal to minus C dAB dYA dx plus YAN. This is equation number 1, as we have discussed earlier, and for equimolar counter current diffusion, Na is equal to minus Nb and is equal to constant. So, N, which is equal to Na plus Nb, would be equal to 0. Since this is 0, so we can write Na is equal to minus C dAB dYA dx. Assume ideal gas. If we assume ideal gas, that C is equal to total pressure by RT. So, these equations will be Na is equal to minus DAB PT by RT dYA dx. So, this is equation number 7. Now, if we use the boundary conditions at x is equal to x 1, y a will be y a 1, at x is equal to x 2, y a will be y a 2. So, using this boundary condition, we can write flux will be equal to dAB PT by RT x 2 minus x 1 into y a 1 minus y a 2, and hence we can write dAB by RT x 2 minus x 1. If we multiply it by the total pressure, this will be partial pressure P A 1 minus P A 2 of component A. So, this is equation 8. Now, let us have an example where the equimolar countercurrent diffusion is occurring. Consider the similar gas as we have considered in the example 1. CO2 is diffusing at steady state through a straight tube of 0.5 meter long. The distance is given with an inside diameter 0.05 meter, which contains the nitrogen gas at 300 Kelvin and 1 atmosphere pressure. The partial pressure is given at 2 points. At one point 15 kilopascal and other point is 5 kilopascal, and the diffusion coefficient dCO2 nitrogen is given 4 into 10 to the power minus 5 meter square per second, and we have to calculate molar flow rate of component A, that is CO2, and the molar flow rate of component B, that is N2. Let us assume ideal gas, and then we know the flux equation in CO2 will be equal to dCO2 into the nitrogen RT x 2 minus x 1 into partial pressure of CO2 at 0.1 minus partial pressure of CO2 at 0.2. So, the data which are given: diffusion coefficient of CO2, nitrogen 4 into 10 to the power minus 5 meter square per second, pressure is given PT, which is 1 atmosphere, 101.3 kilopascal, which is equal to 1013 into 10 to the power 5 Pascal, and temperature is given, which is 300 Kelvin, and the distance x 2 minus x 1 between 2 points is 0.5 meter. The partial pressure of CO2 at point 1 is 15 kilopascal, which is 15,000 Pascal, and partial pressure of CO2 at point 2 is 5 kilopascal, which is 5,000 Pascal, and R is given, R is known to us 8314 Pascal meter cube K mole Kelvin. Now, if we substitute in these equations, the flux in CO2 will be equal to diffusivity 4 into 10 to the power minus 5 meter square per second, and RT 8314 Pascal meter cube by K mole Kelvin into 300 Kelvin into 0.5 meter multiplied by the partial pressure difference 15,000 minus 5,000 Pascal. So, if we calculate, this will be equal to 3.21 into 10 to the power minus 7 K mole per meter square second. So, this is the flux of CO2. We have to calculate the molar flow rate of CO2. So, to calculate the molar flow rate is equal to flux of CO2 multiplied by the cross sectional area of the tube, which is A. Internal diameter is given, say di is 0.05 meter, and then we can calculate the cross sectional area A is equal to pi di square by 4 is equal to pi by 4.05 square meter square, which is equal to 1.96 into 10 to the power minus 3 meter square. So, the molar flow rate CO2 is equal to flux we have obtained in earlier, which is 3.21 10 to the power minus 7 K mole per meter square second. So, 3.21 10 to the power minus 7 K mole per meter square second multiplied by the cross sectional area 1.96 10 to the power minus 3 meter square. So, if we multiply, this will cancel out, and then it will be 6.29 10 to the power minus 10 K mole per second. Similarly, for component B, that is nitrogen, we can calculate N nitrogen is equal to D N2 CO2 divided by RT X2 minus X1 partial pressure of N2 at point 1 minus partial pressure of N2 at point 2. Now, P N2 at point 1 will be P T minus P CO2 point 1, which is 101.3 minus 15 kilopascal, which is equal to 86.3 kilopascal and 86300 Pascal. P N2 at point 2 is P T minus P CO2 at point 2 is 101.3 minus 5 kilopascal is equal to 96.3 kilopascal, which is equal to 96300 Pascal. We know that for equimolar counter current diffusion, the CO2 N2 is equal to d N2 CO2. So, we can use the same diffusion coefficient and calculate the flux N2. If we incorporate this data, so it will be minus 3.21 into 10 to the power minus 7 kmol per meter square second. Similarly, the molar flow rate of N2 we can calculate minus 3.21 10 to the power minus 7 kmol per meter square second into 1.96 into 10 to the power minus 3 meter square. So, it will be essentially same value, but with a negative sign, which indicates that the flux is in opposite direction compared to the carbon dioxide. So, kmol per second. So, another type of diffusion occurs where the component are not equimolecular in nature. So, there are many situations, they are non-equimolar counter diffusion. Let us consider the following reaction. Twice A plus B forming twice C, where 1 mole of A diffuses towards B, whereas 2 moles of B diffuses back or in opposite direction. So, in this case the Na will be minus Nb by 2, and we can derive the governing equations considering our basic equations. So, this is end of discussion of lecture 2, and in the next lecture we will consider the steady state diffusion through non-uniform geometries. Thank you.